In pursuit of sharing technical knowledge and just to gear up the new generation of engineers, myself Pranav is here to deliver today's presentation, Power Transformer Part 28. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with OIP bushing test tap and potential tap. As a precautionary measure against any major failure, the condition of bushings are to be routinely monitored by performing capacitance and power factor tests on OIP bushings throughout their service life. For bushing offline power factor testing, a test tap having with closing and grounding cap is made to provide on the bushing flange to have a conception for an external potential. Also, as of customer's requirement, voltage tap or potential tap along with closing and grounding cap is there to be accommodated at the bushing flange as well. To form a test tap, an insulated wire is first to connect onto the outermost layer of conducting foil of condenser core, and its external end is then to be crimped to the test tap stem. That test tap stem must be embedded in an epoxy molded bush so as to make it insulate from mounting flange of the bushing. Just to make the lead externally accessible, it is therefore taken out of the condenser core with a device which is termed as test tap of bushing. A spring-loaded test tap cover is implemented in such a way that the test tap stem or stud would have been connected to mounting flange directly while the test tap cover is at tightly closed position. In this situation, test tap in ground potential is thus to be ensured as because the mounting flange in turn gets connected to transformer tank, which is always be arc condition. See the diagram of potential tap and test tap. During equipment shutdown, this tap cover is made to open for necessary testing and measuring the dissipation factor, that is tan delta, and capacitance of the condenser core of the respective bushings. In either case, a potential tap or test tap can be used for offline power factor testing. It is of much importance to close the test tap cover tightly after completion of testing the bushing at site. If the cap would have been somehow loosely fitted, then the outermost conducting layer of bushing condenser may have a chance to remain floating without getting grounded through the test tap. By mistake, if the bushing is put in service keeping the test tap cover not properly tightened, then a possible arcing may have to occur between the test tap lid and bushing mounting flange, as due to the voltage developed across the capacitance between outermost condenser layer and the bushing mounting flange lying at ground potential. Such type of occurrence may ultimately lead to bushing failure having with severe system fire hazard. The bushing insulation system in case of capacitance graded bushings has two capacitance components. Capacitance between the centrally placed highly voltage conductor and the test tap of the bushing, that is C1. Number two, capacitance between the test tap and the bushing mounting flange, that is C2. Centrally placed HV conductor, that is the insulation system of capacitance graded bushing with multiple layers of capacitors formed between the centrally placed HV conductor and the test tap can be represented by a single equivalent term C1. Number two, test tap itself is isolated from the grounded flange, and this insulation can be represented by the term C2. Centrally placed HV conductor with test tap, another is from test tap to grounded flange. From figure 118, it can be concluded A, as the total capacitance between the centrally placed HV conductor and the test tap of the bushing is C1, so individual capacitance between each of the conducting layers in condenser core can thereby be represented by NC1, where N is the number of capacitors formed in condenser core. Therefore, C1 insulation system also represents the total capacitance as formed between the multiple layers of the condenser core, which includes the capacitance formed up to the potential tap. C, while the test tap cap at open status and is isolated from the grounded flange, then this insulation is therefore to be represented by the term C2. Hence, C2 insulation system of a bushing with a potential tap that includes the outermost oil impregnated kraft paper layer of the condenser core, as well as insulation between the potential tap and the grounded flange. See the diagram of the potential tap with tap cover and ground flange. Conclusive part of bushing test tap. OIP type bushings are always be susceptible to failure due to aging, contamination, and deterioration of its composite insulation system. Main purpose of providing test tap is to carry out offline measurement of the bushing's inner insulation, and the corresponding value would help to evaluate the basic changes of the dielectric properties in the inner insulation. Therefore, test tap is mainly for to carry out offline measurement of the bushings inner insulation, and the corresponding value would help to evaluate the basic changes of the dielectric properties in the inner insulation with their service life. So, a measurement of the loss factor tan delta can also be determined by using the test tap. Test tap is so designed that when its top cover is tightly closed, then a connection between the test layer and the mounting flange would have to be automatically established. It is to be noted that the mounting flange is always be at the ground potential. Before put the bushing in service, it is prior to have a check for proper tightness of the test tap cap to avoid poor contact and resultant heating. During installation, it is also recommended that necessary checking must be carried out to determine proper grounding of bushings with their corresponding grounded test tap and potential tap provided for power factor test electrodes. These cover lids will be in open condition while at time to have offline measure of the voltage between the test layer and the flange, or for the purpose of monitoring partial discharge criteria. However, the maximum permissible voltage between the test layer and the flange is limited to 1.5 kV. All sorts of testing for determining the health of bushings are to be carried out as per the prescribed limits stated at IEC 60137 standard. For online health tracking, it is advised to carry out infrared and visual inspections at regular interval. Now start with resin impregnated paper bushings, RIP bushings. Epoxy resin impregnated paper bushings technology has adopted a new concept of an oil-free and thus dry and clean technology, and is characterized by its outstanding technical performance. In OIP bushing, oil impregnated paper bushing technology, the basic configuration of condenser core is mainly wound from paper, and subsequently that has been treated and impregnated with an insulating liquid, generally transformer oil. The condenser core is thereby encapsulated in a high quality electrical grade hollow cylindrical porcelain insulator. The interim space between the condenser core and the cylindrical porcelain insulator is also being filled with the same insulating liquid as that used for paper impregnation, which must have to remain in a liquid phase throughout the bushing's entire service life. So, why OIP bushing is much susceptible to moisture ingress, prone to oil leakage due to worn out shields or mounting technology, defects in mounting technology would have become critical as due to presence of oil. So OIP bushing is much susceptible to moisture ingress, prone to oil leakage due to worn out seals, and mounting technology would have become much more critical as due to presence of oil. Since 1960, developing and implementing under vacuum resin impregnated paper technology for high voltage bushings has adopted a new class of insulating material having with improved thermal and electrical performance, which obviously differs significantly from oil impregnated bushings technology. The basic configuration of condenser core is mainly wound from crepe paper, which is subsequently vacuum dried, impregnated with epoxy resin, and cured. Base material of crepe paper is of 100% unbleached sulfate conifer wood pulp. Insulating crepe paper is actually made of insulating kraft paper with creping and has a stable electrochemical index with having excellent dielectric strength. The creping process of the kraft paper would have to avoid and add 200% more strength and elasticity in respect of mechanical as well as cross mechanical directions, and hence becomes more resistant to breakage. Again, I repeat, the creping process of the kraft paper would have to add 200% more strength and elasticity in respect of mechanical as well as cross mechanical directions, and hence becomes more resistant to breakage. Condenser core is thus to be comprised of resin impregnated paper body with inserted aluminum foils at calculated positions to give a grading of electric field, and is made to wrap up on either centrally placed tube or solid conductor. Once the core formation is completed, subjected paper core is inserted into a metal cylinder, which is then to be filled completely with epoxy resin under vacuum. This process has made the unit a void-free solid condenser core body, which is thus to be machined to its final dimensions, and a mounting flange is then to be fitted. The upper section of the condenser core, as being exposed to open atmosphere while in installation, so this section is thereby made to encapsulate in a high quality composite insulation with silicone rubber or porcelain insulator. The empty or intervening space between the condenser core and the insulating cover would have been filled up with an insulating material like polyurethane foam or compressive dry filler, mica gel, etc. The lower section of the condenser core is being kept inside the oil filled transformer tank. So, typical RIP bushings do not require an additional external lower insulators. So, for the reliability as compared to OIP technology, the dry RIP bushing technology is rather compatible to have a range from 15 kV to 765 kV. But especially the case for high and extra high voltage classes ranging from 230 kV and above. Some issues are being exhibited regarding moisture ingress in the exposed lower oil side section during long-term storage. So as to protect RIP bushings lower section, it is therefore to be recommended for arranging oil-filled or gas-filled tanks while kept for long-term storage. To eradicate the certain risk of moisture ingress, an improved version of implemented which is very similar to RIP technology with the exception of using a non-hygroscopic polyester synthetic material instead of crepe paper and is termed as the resin impregnated synthetic or RIS type bushing. That is resin impregnated type synthetic. Resin impregnated synthetics is the latest technology so far been achieved by the HB bushing manufacturers, where the epoxy resin, as similar to RIP technology, is used for the main insulation material. See the diagram of main components of RIS type bushing as well as RIP type bushings. Air side shield for voltage class 420 kV and above, and air side shield is also provided for preventing corona discharges. Most important. Also, in RIS technology, no additional insulating cover is implemented for the lower section of the condenser core, which is kept totally exposed to oil. Most important. Also in RIS technology, no additional insulating cover is implemented for the lower section of the condenser core, which is kept totally exposed to oil. The upper section of the condenser core as being exposed to open atmosphere, so this section is thereby made to encapsulate in a high quality composite insulation with silicon rubber, which is either extruded or molded directly onto the RIS condenser core. On bottom side of the bushing for both of RIP and RIS technology are equipped with electrical shield, generally made of aluminum, and the shield is also to be epoxy resin insulated. While transformer in service installed bushings with electrical shield that has to ensure a smooth electrical field grading. Each bushing must have provision with a standard test tap which is installed and connected at the outermost aluminum layer of the bushing mounting flange, and that would have been automatically arched with the cap as screwed tightly to cover up the test tab. That is same as OIP bushing test tab. Characterization of oil paper and resin paper capacitive bushing. Features. Technological configuration. For OIP, basic insulating medium is oil and that remains in a liquid phase throughout its entire life. For RIP bushing, using an oil-free, thus dry and clean technology. Condenser core, oil impregnated kraft paper body with inserted aluminum foils in precise locations to build up capacitive grading of electric field. Core is impregnated with transformer grade mineral oil under vacuum and heat. resin impregnated crepe paper body with inserted aluminum foils in precise locations to build up capacitive grading of electric field. Core is impregnated with epoxy resin under vacuum and heat, which creates a void-free condenser core body that becomes completely solid. Bushing housing equipped with porcelain insulator, equipped with porcelain or composite shell of silicon insulator. Filling material. Space between condenser core and outer porcelain insulator is filled with transformer grade mineral oil. Space between condenser core and outer composite insulators is filled with polyurethane foam or compressible dry filler mica gel. In dusty environment, as a porcelain insulator, so frequent cleaning is obvious. Due to hydrophobicity of silicon housing, so cleaning is usually not necessary. But if you use porcelain insulator, then you have to clean frequently in case of RIP bushing. Power factor and partial discharge limits at 20 degrees centigrade. Acceptable IEEE standards. Power factor limits as measured for C1 insulation system is 0.50% and the 1.5 times line to ground partial discharge limit is 10 picocoulombs. Power factor test indicates the amount of contamination and the capacitance value indicates the physical changes in the conductive layers. Increase in power factor indicates the amount of contamination, while increase in capacitance indicates if any layers have been shorted out. Acceptable IEEE standards for RIP bushings. Power factor limits as measured for C1 insulation system is 1% and the 1.5 times line to ground potential with partial discharge limits is 25 picocoulomb. Both the limits are 2 times higher than OIP within the IEEE standards. The capacitance value derived by the power factor test are the main indicators of a physical change inside the bushings. Dissipation factor or loss tangent, that is tan delta, susceptible to moisturizing rays. So there will be chance of deviation of the tan delta value compared to the value as prescribed, usually be 0.45% or lower in case of OIP bushings. For RIP bushings, usually the range of tan delta value will be 0.35% or lower. That is, a larger tan delta value will indicate moisture level in the paper and amount of contaminant in the insulation system, and obviously of lower insulation resistance. Change in oil level at oil level gauge. Once the oil drops below the paper layers of the condenser core, then internal partial discharge would have to start, causing to damage the paper while the bushings is energized. Bushing oil sample analysis is also to be recommended for checking the bushing's health. It is not relevant for in case of RIP bushings as because the impregnation in RIP technology is carried out via a curable epoxy resin to form a solid condenser core. Insulation class as per IEC standard 60137. Class A in case of OIP, that is up to, it can withstand up to 105 degrees centigrade temperature. For RIP bushing, high thermal strength with insulation class C, that is up to 120 degrees centigrade. We know the insulation class YA, EB, FHC. You must have to remember the class of insulation YA, EB, FHC. YA, EB, FHC. Ignition level, flammability, and explosion risk. For OIP bushing, a large amount of energy is contained within the oil, which in the event of an explosive failure, there may be a chance of spraying over the equipment and associated equipment rather, and may have to instigate causing multiple case of fire and may expose a large surface to possible ignition. Much more vulnerable in lightning strikes or other factors that can also trigger explosive failure. For RIP bushings, flammability and leakage issues related to oil have effectively eliminated in RIP technology, which allows to lower the risk of bushing failures. Time to ignition is 10 times longer for the components as compared to OIP bushings. Compressible dry filler mica gel as used is likely to prevent ignition. Weight of the bushing. Normally, OIP bushings are configured with porcelain insulators both in upper air side and lower oil side. Of the same voltage class, porcelain OIP bushing is higher weight. Whereas for RIP bushing, weight is approximately 50% of porcelain OIP bushings. Transportation. Handling and transportation both are much more sensitive. To avoid from certain mechanical impact, specific packaging and transportation procedure should have to be followed, or otherwise severe physical damage may happen, or certain damages may occur. Comparatively less weight in case of RIP bushings of dry insulation, necessary handling and transportation both are more or less easier. Mechanical strength. Having with moderate mechanical strength and comparatively much lower capability, to withstand mechanical stress if imposed. But in case of RIP bushings, comparatively much higher and can have to withstand higher mechanical stress. Seismic withstand capability as per IEEE 693-2005 standard, very low seismic performance withstand capability. Seismic performance level is quite high in case of RIP bushing. Installation and commissioning. General procedures and guidelines as recommended by the OEM should have to be followed with special care and caution. For OIP bushings, certain restriction has been imposed for maintaining the usual installation conditions of OIP bushings as because it is oil insulated. Number one, resting the bushing always be in vertically up position. Mounting angle would have to be maintained 30-degree equal or more than 30-degree, maximum to vertical. Insulation is provided by a combination of porcelain shell and transformer oil, where oil has made the porcelain surface creepage strength much more higher than that of air. So, oil level is an important factor and that must have to maintain as per acceptable requirements. Before installation, you have to check it. As of porcelain framed, so bushing are to be handled with extensive care. 5. Bumps, impacts, and shocks must be avoided. And in case of RIP bushings, as because of oil-free dry type bushings, so installation can be made at any angle, whether vertically or horizontally. However, the gap in between the insulating body and the external insulator is filled with thermal compound, so bushings can be operated at any installation angles of up to 30-degree from the vertical. Comparatively, installation time is much less as compared to OIP bushings. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments, feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want to know, then let me inform in the comment section. Thank you. Thank you for patient hearing.